Hello all, today we will solve a one-dimensional bar element using FEA. Is the lecture number 5. Hope you have gone through other lectures in this series. If you haven't, study the previous lectures carefully, then go to this lecture, that is lecture number 5. In the last lecture, we have seen the finite element equation for one-dimensional bar element. F is equal to K into U. That is the equation for one-dimensional bar element as shown here as equation number 1. And for a two-noded bar element, F will become F1, F2 in braces and U will become U1, U2 in braces. Then, substituting the values in equation number 1, it will become F1, F2 in braces equal to AE by L into stiffness matrix into U1, U2 in braces. U1 and U2 are the displacements at node 1 and 2. F1 and F2 are the forces at node 1 and 2. A is the area of cross section. E is the Young's modulus. L is the length of the bar. We are going to solve a simple problem using finite element method. An example is shown here from the textbook. A steel bar of length 800 millimeter is subjected to an axial load of 3 kilonewton as shown in figure. Find the elongation of the bar neglecting self-weight. The picture is shown here. This is the bar. Length of the bar is 800 mm. 3 kilonewton weight is hanging at the end of the bar. Self-weight of the bar is neglected. Question is, what will be the elongation of the bar? We know some other methods to solve this problem using the formula, but now we have to solve it using the method of FEA. The question also given, take E is equal to Young's modulus equal to 2 into 10 raised to 5 Newton per millimeter square, area of cross section capital A of the bar 300 mm square. So first we will write the given things. L is equal to 800 mm, load F is equal to 3 kilonewton, Young's modulus E equal to 2 into 10 raised to 5, area of cross section capital A equal to 300 mm square. Question is to find the elongation of the bar small u. Small u is the letter used for displacement or elongation. So first we will divide the bar into two elements as shown in figure. So the bar is divided into element number 1 and element number 2 with the length, equal lengths 400 mm and 400 mm. The 800 mm is divided into 2 and the weight 300 into 10 raised to 3 Newton is acting at the end of second element. Also we can see nodes. Node 1 is at the fixed support, 2 is between 1 and 2 elements, 3 is at the end of the bar where the load is acting. So 2 elements and 3 nodes. A convention to represent elements and nodes are given here, that is number with circle denotes elements, number without circle will be representing nodes. So the picture is shown here, 2 elements, 3 nodes. U1, U2 and U3 are representing displacements at node 1, node 2 and node 3. We need to find out these values, that is a question. For a one-dimensional two-noded bar element, the finite element equation, we know this equation. We will substitute the values of element 1 and element 2 separately in this equation, and then we will combine this equation, combine the values of both element 1 and 2, and we will find out the result. Let us see how it is done. First we will go to element number 1. Element number 1 is shown here from this picture. U1 and U2 are the displacement, L1 is the length 400. So we will take element number 1 and finite element equation for element number 1 is here, and substituting the values A1 E by L1, we will get 300 into 2 into 10 raised to 5 by 400. These are the values for element number 1, 1 minus 1 minus 1 1, U1 U2, F1 F2 for element number 1. Then simplifying this part, we will get 150 into 10 raised to 3. Then since it is the first problem, for clarification, the stiffness matrix elements are shown with the notation. A11 means first element, first row, first column element. A12 means first row, second column element. A21 means first second row, first column element. A22 means second column, second row element. U1 U2 F1 F2. That is given as equation number 1. Then we will go to element number 2 with the nodes 2 and 3. This is the element number 2. U2 is the displacement at 2. U3 is the displacement at 3. Finite element equation here, substituting A2 and L2. E is same for element number 1 and 2. U2 and U3 are the displacement. So U2, U3 get to F2 and F3 are the corresponding forces. We will substitute these equations. We substitute the values of element number 2 in this equation. Substituting the values of element number 2, 300 into 2 into 10 raised to by 400. Same values as the element number 1. U2, U3, F2, F3. Simplifying, we will get again 150 into 10 raised to 3. Then A22 is the first element because it is the node numbers. 2 and 3 are the node numbers. So this element, first element in the stiffness matrix will be A22. Second element will be A23. Third element will be A32, 33. U2, U3, F2, F3. So the notation, look at the notation again, A22, A23, A32, A33. Why only 2 and 3? Because nodes are 2 and 3 in element number 2. No node is represented as 1 here. So A22, A23, A32, A33 represents the position of the element. Next, that is given as equation number 2 here. Next step is assemble the finite element, that is assemble the finite element equations 1 and 2. When we assemble the finite element equations, we will just add the matrix. So first the left side is common, that is 150 into 10 raised to 3, that is taken as a common. Then we will add the two stiffness matrices from equation number 1, that is this, and equation number 2, that is this. Okay, so we have added 0 here, 0 here, because we have added like this. A11 is 1, A12 is minus 1, A13 is not there, so 0. Then the next row, A21, that is minus 1, A22. A22 is common to equation number 1 and 2. In the previous equation, that is equation number 1, A22 is 1. That is the first one here, plus 1. That one is from here, because A22 is common for equation number 1 and 2. So 1 plus 1 came here. Then A23. A23 is minus 1. A23 is this minus 1. Then A31 is not there, so that is 0. Then A32. A32 is this minus 1. And then A33, that is this one. So only one common number, that is A22. So 1 plus 1 came here. Hope you understood how we have added the two stiffness matrices from equation number 1 and 2. Then U1, U2 and U3 are the three displacements used. So U1, U2, U3. Then F1, F2, F3 are the three forces on the right hand side. So combining 1 and 2, we will get this equation. So 150 into 10 raised to 3. When simplifying, 1 minus 1 0 minus 1, 2. 2 is this 1 plus 1, minus 1, 0, minus 1, 1. This is known as K global stiffness matrix. After combining element stiffness matrix, we will get global stiffness matrix. Then U1, U2, U3, F1, F2, F3. That is equation number 3. So we got the finite element equation for the bar. Note, the rod has 3 nodes. Each node has single degree of freedom. So the global stiffness matrix K size will be what? 3 into 3. This is a 3 into 3 matrix. Why? Because in the question we have divided the bar into 3 nodes, 1, 2 and 3. So there will, when we simplify the element equations, we will get the K global. Now we will check whether our stiffness matrix, that is K global, whether it is a correct stiffness matrix or not. We know that from the stiffness matrix properties, to satisfy to become a stiffness matrix, 2 conditions are there. One is it should be a symmetric matrix. 2 is the sum of elements in any column is equal to 0. So this is a symmetric matrix. If we interchange rows and columns, we will get the same matrix, and sum of elements in each column, 1 minus 1 0, that is 0, minus 1 2 minus 1, that is the sum is 0, 0 minus 1 1, the sum is 0. So it satisfies the stiffness matrix properties. So so far our procedure is correct. So we will go to the next step, that is boundary conditions applying boundary conditions. We need to apply boundary conditions in the equation number 3 to solve for u1, u2 and u3, otherwise we cannot solve. So in the question some boundary conditions are given. First is the displacement at node 1 is 0, because u1 equal to 0, because u1 is, where is u1? That is at node number 1. At node number 1 it is fixed, so it cannot move, so u1 equal to 0. Then applying the boundary condition 2, that is the question 3 into 10 raised to 5 Newton load is acting at node number 3. We have given that and as node number 3, so we can say F3 equal to 10 into 10 raised to 3 Newton. Self weight is neglected, that is given in the question. So F1 and F2, that is forces acting at node number 1 and 2, can be given as 0. So these are the boundary conditions. So substituting u1, f1, f2 and f3 values in equation number 3. After substituting the values, boundary conditions, we will get this equation. u1 became 0, u2 and u3 are the unknowns. We have to find that f1, f2 are 0, f3 is 3 into 10 raised to 3. Equation number 3, we will get this. Now we have to solve for u1 and u2, u3 and u2. So there is a simple method for solving this equation. We need to multiply this matrix, square matrix K, into this column matrix of U. This is a 3 into 3 matrix, this is a 3 into 1 matrix. We can use the conventional method, but we can simplify it in a better way. That is, since U1 equal to 0, we can neglect first row and first column of this K, and we can neglect first row of this U matrix. Also we can neglect first row of this F matrix. So we will get this equation 150 into 10 raised to 3 by neglecting first row here, first column here, 2 minus 1 minus 1 1, then 0 is neglected, u2 u3, then this 0 is neglected since it is first row, 0 3 into 10 raised to 3. Why we have neglected first row and first column? Since u1 equal to 0 here, even if you multiply using first row and first column, since this first member is 0 here, that will become 0. Then we will multiply this square matrix into this column matrix. 150 into 10 raised to 3, then 2 into this u2 plus minus 1 into u3. That is a method we know. that is equal to this 0. Then 150 into 10 raised to 3 in then first second row into this column minus 1 into u2 plus 1 into u3 equal to this 3 into 10 raised to 3. So we got equation number 4 and 5. By adding this 4 plus 5 we will get 150 into 10 raised to 3, that is common. U3 will be cancelled into u2 equal to 3 into 10 raised to 3. So u2 is the only unknown. We will get u2 equal to 0.02 mm. Substitute u2 value in equation number 4, that is this equation. We will get the value of u3. u3 is the only unknown there, that is 0.04 mm. So we got two unknowns, u2 and u3. u2 is 0.02, that is a display when a weight of 3 into 10 raised to 3 is hanging at the end of the bar as shown in that figure. We will get a displacement of 0.02 mm at node number 2, 0.04 mm at point number 3. So what will be the total elongation? Total elongation will be at the end of the bar, that is u3, 0.04 mm. So this is the answer we got. Next step is verification of the answer. We will use the conventional method of finding the total elongation delta L equal to PL by AE, that this equation we have studied earlier for finding the elongation of a bar. Substituting the values in this equation, total load, that is P equal to 3 into 10 raised to 3 given the question, acting at the end. Total length is 800 mm for the bar. Area of cross section of the bar is 300. 2 into 10 raised to 5 is the Young's modulus. So we will get delta L equal to 0.04 mm. That is the total elongation of the bar. Total elongation of the bar is equal to elongation of the bar at node number 3 using FEA method. So both are same. So we verified our method with the conventional method. So today we have studied a simple problem of one-dimensional bar element using finite element analysis method. This is a simple problem. So study this problem by writing it down and understanding the method to solve one-dimensional problems using FEA method.